Welcome everybody to my presentation about segmentation of buildings based on high-resolution PSI point clouds. My name is Philipp Schneider. I'm with the Institute for Photogrammetry at the University of Stuttgart. The motivation for this work is the segmentation of high-resolution point clouds, PSI point clouds, into substructures that represent rigid parts of a building. And this should later be used to integrate this PSI technique into building information monitoring systems. I will firstly shortly explain the PSI principles, then I will explain my geocoding approach and that I used for the label transfer. Then I will explain the deformation space and the clustering method I used here. And finally, I will show some results. So PSI is a differential synthetic aperture radar technique. And by comparing the phase of synthetic aperture, of a stack of synthetic aperture radar images relative to a master image, very small movements can be detected. This works especially well for urban areas, since metal objects and buildings act as good reflectors. On vegetation and water, for example, the phase would decorrelate and we wouldn't get a measurement point. The product of PSI, of this analysis technique, in the end will be a 3D PSI point cloud and the deformation history for each point. How does this look like? So here I show the colorful points are PSI points, and I overlaid them with a 3D city model. And you can nicely see how the points are distributed on the houses, but there are no points in this vegetated area. There are also no points here because there's an ongoing construction, and if things are changing too quick in the scene, in the radar scene, we also won't get points because there's no steady phase change, basically. Here you see again there's no points here in the area that changes very quickly or in the vegetation, but we get a lot of points on the houses. The interesting thing about these point clouds is that you receive a time series for each point. And the time series represents the deformation history of this point with millimeter accuracy. So here you see I was using images over the time span of 4 years, and you see how some points here on this building moved in these 4 years, and the accuracy is really millimeters, so you can see annual movements or some linear trends in this movement. Since we want to investigate on single buildings, we use OpenStreetMap building footprints to segment the PSI point cloud into building instances. And for this, we choose a reverse geocoding approach that first transfers these footprints into the SAR image geometry, because we know the origin of each PS point in the SAR image, and then we can use that in the SAR image to determine where is each point coming from. And this helps to solve some ambiguities, especially if buildings are very close. The accuracy of the coordinates of the PSI point clouds are in the range of 1 meter, so we would get ambiguities when buildings are very close to each other. So whether we simply transfer the the labels into the SAR image geometry, and then assign the PS points in the SAR image. So a quick overview about the SAR image geometry. Each point in a scene is mapped based on the distance or the range from the satellite, and this will lead to layover and foreshortening effect in the actual SAR image. So you see how this building here seems to fall over towards the satellite. This is called layover. In reality, as you see the building here, this building is the same here actually, is falling or laying over this street. To compensate these effects, geocoding, a process similar to autophoto generation, is used. With the help of a precise digital surface model and the satellite orbit parameters, a geocoded image in the world coordinates can be produced. And we use commercially available geocoding software to not geocode the range azimuth image, we geocode a lookup table with the precise digital surface model, and thus then gives us a relationship from the real world coordinates to the satellite image coordinates. So this we can use then later to generate the label maps in SAR geometry. So we start with the labels in OpenStreetMap building footprints and the digital surface model, and now we have the labels in SAR geometry. You can nicely see how, for example, this is the house that leans over the street. It's also leaning here in our labels, like in the SAR image. And this now we can use to create this labeled PS point cloud. So we know all the PS points in our point cloud that are in one building. So we can now start to investigate into single buildings. So now we have all the PS points on a single building and the time series associated with each PS point. And what you could do now is draw, I call it deformation space, where you have one dimension for each date of deformation. So here I only have 3 deformations, so I end up with a 3-dimensional deformation space because it's easier to visualize. But in the work we actually had 132 deformation dates. And you now see already these clusters forming here. So you have some points that are somewhere up here in this space and some points that are somewhere down here in this space. And you can also see these points here in the time series. The assumption here is that points that are on the same rigid structure show a correlated deformation behavior. For example, here all the points on the roof are moving in a similar fashion, and all the points on the facade move in a different but similar fashion to each other. And we find them by clustering in this deformation space. The distance metric we use to compare 2 points, so how similar they are in deformation space, is the sample correlation, or 1 minus the sample correlation. And this will give high values for points that are strongly correlated and low values for points that are not correlated. And this in contrast to, let's say, an Euclidean distance, considers points as close if they show a correlated movement. And this is exactly what we expect from points that are on the same rigid structure. So clustering in these 132 dimensions is quite unreliable and comes with various curse of dimensionality problems. Therefore, we use a t-distributed stochastic neighborhood embedding, TSNE, and the previously mentioned distance metric to embed this high-dimensional space into a 2-dimensional space while preserving the local neighborhood. So we go from this high-dimensional deformation space into a 2-dimensional space where the points have the same neighbors they had in the high-dimensional space. So here I show some embedding of this. So we have 2 clusters here, but there's also a lot of points around them that are not, they don't show basically a correlated movement to any other neighboring points they have. So we use the core distance graph, in the median in the core distance graph, to filter out points that are not part of these clusters. And afterwards we use dbScan and also the core distance for the hyperparameter epsilon to cluster in this space. So this is the full workflow. We start with PS points on a single building and then use TSNE to embed the deformation space into 2 dimensions. We use the core distance graph to estimate a threshold for the dbScan later and also to find non-cluster points. And we finally use the dbScan to cluster the embedded space. And then we have a step where we discard outliers from the clusters based on the correlation distance for each point to the cluster center. So not in the deformation space, but not in the TSNE embedding, but in the deformation space. And finally, we merge clusters if they are very similar in the deformation space, but not in the TSNE, because TSNE tends to rip apart clusters sometimes, or points that are kind of close, but actually then end up very far in the embedding space. So this leads to the results. Here we see the embedding of a deformation space with the clusters, and on the left-hand side you see the distribution of the points in the real world. You can see, for example, this tower here is represented by these two groups, and the lower part of the building is represented by different groups. So there's really a segmentation of the building going on just based on the deformation time series. If you look at these time series, you can now further investigate in how each of the clusters was behaving. So if we look at this here, for example, it shows a slight uptrend over the years, where other parts of the building, let's say this turquoise here, is just showing a seasonal trend. This is an example from another building. This is a bit bigger, and you see how the different sections of the building show different clusters in the embedded space, and also the time series for each part of this building. What's really interesting here is that you can see an annual movement, so you see these periodics ups and downs. So for this reason I plotted the temperature in the city over year, and you really see how some parts of the building are going up with the temperature, and some parts of the buildings are going down with the temperature. You see here this part is going down in summer, and this part is going up in summer. So, conclusion and outlook. We presented a nonlinear dimension reduction and clustering technique that can segment PS points on buildings into plausible substructures without any spatial information. Future work, and actually work in progress now, is to use a distance metric that combines the correlation and the Euclidean distance, so we actually take in account spatial information. Also, the next step is now to use actual BIM representation of buildings to confirm the structures we found in our results. And another interesting thing is we could analyze clusters relative to each other so for example, this cluster and their movement relative to each other, to come up with a risk assignment of this part here. So this could lead to an automatic citywide building risk assignment. So thank you for your attention. I would like to thank the DLR for providing the TerraSAR X images, also the LGL Baden-Württemberg for the ALS data, and the Amt für Umweltschutz Stuttgart for the temperature data. Thank you very much.